All right, let's jump right into this explainer. Today, we're uncovering the hidden clues in mathematical investigations. And we're really going to be treating mathematics a lot like an archaeological dig, because we aren't just looking for a single isolated number, right? We are working methodically, layer by layer, dusting off the clues to reveal the perfect, structured answer that's hidden just beneath the surface. We're going to look at two fascinating investigations from our source material today. One is highly concrete, and the other is wonderfully abstract. And as you'll see, we'll discover exactly how structured thinking leads us straight to universal truths. Let's get started. To get our logical gears turning, I want you to imagine a television show puzzle. Contestants are standing by 12 treasure chests, and they're all arranged in a circle. Now, the goal is pretty straightforward. Find the single chest containing the hidden treasure. But here's the catch. You don't just guess. The game operates on a very specific, alternating elimination rule. So the question we are trying to answer as mathematical detectives is this. Based on this alternating rule, where exactly is that treasure hiding? Section 1. The Hidden Treasure Puzzle, Process of Elimination. Okay, let's look at the exact steps provided in our source to understand how a seemingly simple rule can create a really complex cascading effect. The absolute crucial point here is following the exact rule sequence. You cross out the first chest, and then you continue to cross out alternate chests. So picture it. You look at chest 1, and you eliminate it. Wham, it's gone. You move to chest 2, but, and this is key, you leave it alone for now. Then you move to chest 3, and you eliminate it. Chest 4, leave it. Chest 5, eliminate it. You are simply establishing a steady alternating rhythm. Cross one out, skip one. Cross one out, skip one. Make sense? Now, what's really interesting about this is that the process doesn't just stop when you hit chest 12. Because the chests are arranged in a circle. Reaching the end of the line just means you're right back at the beginning. The source explicitly notes that this pattern involves looping around the circle multiple times. And here's where it gets tricky. As chests are eliminated, those skips start covering the empty spaces where chests used to be. So the gaps get wider, the logic gets a little tighter, and you have to keep perfect track of your alternating rhythm as you circle the island again and again. And this brilliantly illustrates how a systematic, alternating elimination sequence ultimately narrows down the circle to just one final winning chest. By rigorously applying a simple rule over and over again, the chaos of 12 possibilities is chiseled down to absolute certainty. You don't need luck to find the treasure here, you just need to trust the mathematical process of elimination to lead you directly to the prize. Section 2. Planes and Crossing Points, Transitioning to Geometry.
Having primed our brains with a concrete logic puzzle, we can now pivot to a much more abstract geometric problem. We've seen exactly how rules apply to physical objects like treasure chests, right? But now we are going to apply that same investigative spirit to the dimensions of space itself. Notice how we shift from the highly tangible elimination game directly into analyzing abstract spatial relationships. With the chess, you could practically see the wood and the sand. Now we're dealing with geometric planes. Flat, two-dimensional surfaces that extend infinitely in every direction, and we're looking at how they interact when they cross paths. It feels totally different, but the underlying methodology of investigating a pattern, it remains exactly the same.
So, our new mission as mathematical detectives is to figure out exactly how the maximum number of crossing points changes as we add more planes into the mix. Think about it. If you have one plane, what happens? Nothing really. If you introduce a second plane, they can cross in a line. Introduce a third, and those crossing points start to multiply. We are looking for the absolute maximum number of intersections possible as the number of planes increases. It's like a giant, infinite puzzle.
Section 3. Building an ordered table, organizing the data.
Just like we carefully tracked which treasure chests were crossed out, we need a really rigorous system to track our intersecting planes. Our source material gives us a very clear directive quoted right here. Record the results of your investigation in an ordered table. The text emphasizes that making a table isn't just busy work. It's not just a suggestion. It is the absolute required framework for organizing our results. When you're dealing with abstract geometry that multiplies this rapidly, trying to keep all those numbers in your head is just a recipe for disaster. The table is our archaeological grid, keeping everything perfectly sorted so the hidden pattern can finally emerge.
And here is what that framework looks like. By tracking the number of planes represented by the letter P on the left against the maximum number of crossing points represented by N on the right, we set up the perfect environment to spot the pattern. You'd log the data row by row. One plane yields a certain number, 2 planes yield another, 3 planes yield another. And as you diligently fill out this table, that relationship between P and N will slowly start to reveal itself, transitioning from raw, messy data into a beautiful mathematical sequence.
Section 4.
The algebraic rule, decoding the pattern.
Okay, let's dive into the ultimate synthesis. This is where the whole investigation pays off. It's where we take our observations and turn them into a universal law. The entire investigation culminates in this final step, extracting a definitive algebraic rule that links P and N together permanently. We aren't just looking for the answer for 3 planes or 4 planes or even 10 planes. We are looking for the formula that explains the relationship forever. By looking at the differences between the numbers in our table, we can actually construct an equation. This algebraic rule is the ultimate treasure of the second investigation. It's a compact, incredibly elegant mathematical truth.
Think about this as we wrap up today. Once you possess this algebraic formula, you hold the power to calculate intersections from a million planes without ever having to draw a single one of them. That's a real game changer. But what if the rules of the universe shifted? What if the planes weren't infinite? Or what if, back on that island, we skipped 2 treasure chests instead of just 1? Changing the starting parameters shifts absolutely everything, creating entirely new puzzles to solve. I really encourage you to think about how these structures apply to the world around you, because at the end of the day, mathematical investigation is never just about finding the final number. It's about mastering the thrilling process of discovery itself. So what puzzle are you going to solve next?